Yeah. Okay, got it. Thank you, Nader, for this nice introduction, and thanks for inviting me. It's very nice to have the opportunity to speak here. I will discuss inverse problems and experimental design, and I designed this talk to focus on some not very simple problems, so we can really expose the challenges, and then maybe hopefully we'll have some discussion at the end. So let's see. Okay, yeah. So just to get us oriented with inverse problems, just some model problem, which we'll actually not solve in this talk, but we will do something related. So this is a problem coming from contaminant transport. So if I look at this domain, it's like maybe a cartoon version of an urban environment with some buildings, and if I specify the source of the contaminant, that's that plume of contaminant, and I have governing equations, advection diffusion equation in this case, and then I can predict how that model how the contaminant spreads and diffuses. So that would be the forward problem. In an inverse problem, I would take maybe some measurements of the concentration later in time, and then the one inverse problem of interest is to see if we can go back and estimate where the source of the contaminant was. So estimate the initial state. So that would be an inverse problem. Just some more example. It's a related problem coming from groundwater flow, where we look at the transport of a contaminant in some geological formation, maybe let's say in some aquifer or something. So there is some groundwater carries the contaminant, and again there the goal would be to maybe take some measurements of concentration later in time at some points, maybe some monitoring wells, and see if we can estimate where this contaminant originated. So that's a related inverse problem, just to give us more insight. This nice video, but okay. Another example that I mean, again, it's good to look at some examples. I like examples. This image down there is a kind of a picture we drew of like a subduction zone. That's a problem from earthquake modeling, where you look at a couple of layers of earth, and what happens in a situation like this is when a slip occurs, roughly speaking, an earthquake will happen. And in this particular example of inverse problem, you take GPS measurements of the displacement on the top, on the ground, to estimate where the slip region was. So as you see, I'll just give some examples of inverse problems. These are all governed by PDEs. This last one will be governed by linear elasticity in the simplest case. And so we have some PDE model, and then we have some parameter field that we want to estimate in all this inverse problem. Now, I consider Bayesian framework, where we suppose we have some unknown uncertain parameters. We have some prior beliefs. We model that by a statistical distribution. And what we do, we combine measurement data and governing PDEs in this type of PDE-based inverse problems, and then get the posterior distribution. Hopefully, we have a reasonable point estimate, like the map point, and also reduce uncertainty. So we can make more informed predictions with quantified uncertainties. So in all these things that we discussed, we need data to solve the inverse problem. And obviously, it's desirable to have good informative data, and that leads to the idea of optimizing your data acquisition strategy. Now, in this inverse problems, and also more broadly in statistics community, that's known as the optimal experimental design problem, where you want to optimize how do you take your measurements, or how do you conduct your experiments to do good parameter estimation. Of course, the word optimal has to be specified. The word experimental design, well, we have to specify how do we parameterize the design, and we will discuss all of that. Okay. So let's talk about design. I consider problems of sensor placement that's one class of problems. You can have other type of experiments too. So inverse problem reconstructs uncertain parameters using sensor measurements in this case. OED says, where do I put the sensors? And well, you can formulate that problem in different ways. One way is to say, well, maybe I have a grid of possible places to place sensors or big monitoring wells, or where I can put measurement devices. And I want to select a subset of an optimal subset of those candidate sensor locations. So now, so I have this candidate locations x1 to xn. Now, in time-dependent problems, you can also have observation times, but let's just stick to the case where let's say we take one time measurement for simplicity for now. And for each of the sensor locations, we assign a weight that ideally I could formulate experimental design problem as just a combinatorial optimization problem, in which case these weights will have 0, 1 entries. But of course, that would be very expensive to do in general. So one approach, well, of course, we could also do a greedy approach, which is not too bad, in fact. Or if you want to go to gradient-based optimization and such, the one approach is to do a relaxation, allow these weights to take values in interval 0 to 1, and then combine with some penalty method to enforce sparsity of the design. And we will talk about that a little bit later, but you could do something. But for now, the design is a vector of weights. That's how we have formulated it here. And optimal sensor placement is one that minimizes posterior uncertainty. I put it in quotation mark because I have to define what do I mean by that. We have to come up with some measures of posterior uncertainty. We will discuss that too. So common assumptions, and this is of course reasonable, but not always. Typically, when we solve inverse problems, we assume we kind of know everything in the governing equations, and then we focus our attention on a specific source of uncertainty or a specific parameter of interest to estimate. And typically, people assume that there are no other sources of uncertainty other than the inversion parameter, which could be a reasonable assumption because this additional uncertainties might be not that much, and you will have a lot of uncertainties on some inversion parameters, and then you focus on those. But in some other cases, that if the additional sources of uncertainty actually are significant, then that has to be taken into account. So what I want us to talk about is a formulation of OED under uncertainty, and we will, of course, specific cases. It's in general a very difficult problem. We will in fact focus on what we did in this paper from a couple of years ago on design of linear inverse problem, where we can write closed form expressions for measures of posterior uncertainty, and just understand. It's more accessible to understand than also examine the mathematical structure and computational challenges. So that's the aim of the game plan for this talk. Let me see a subsurface flow example. Okay, yeah. So this is we discussed this problem before. So I want to estimate initial state in a groundwater flow problem. Governing PDEs advection diffusion equation. Here, the boundary conditions we have to specify. We'll do that later. But here I want to estimate this M, that the initial state. So use physically that would be the concentration. Kappa is diffusion coefficient. M is the initial state. That's the inversion parameter. And V is the velocity field of this background velocity. Now we use Darcy law, and so the velocity is related to pressure gradient this way, as I wrote. Where C is the log-permeability field, P is the pressure field that you obtain by solving this pressure equation. And here's an example of a velocity field that we superimposed on the corresponding log-permeability field. Now, the OED problem says, where do you take the measurements? But but there's a lot of uncertainties typically with the velocity field. In fact, the problem of estimating the velocity, the log permeability field, which then will give us the velocity field itself, is a common inverse problem. So yes, log permeability is uncertain, so V is uncertain, and yeah, I mean, here we just different velocity fields give the very different dynamics, and so which velocity field should I use when I solve the OED problem, or even the inverse problem for that matter? So, but we are discussing the experimental design. So now we can have a discussion about this reducible versus irreducible, but at the stage of solving this inverse advection diffusion problem, I'm not reducing the uncertainty in the velocity field anymore. So in that sense, I'm kind of stuck with whatever uncertainty model I have for the velocity field. Maybe in the past, some inverse problem has been solved. Maybe we have some posterior distribution from before for the log permeability field, which can give you the velocity. But at the stage of solving the inverse advection diffusion problem, there's nothing much I can do about the uncertainty in the velocity field. So that, in the very practical sense, call it the irreducible uncertainty, because it's that. So in reducible setting, it would be when I'm jointly estimating the parameters, and then maybe I want to focus on another one of them. But that's not the setting here. So we want a sensor placement that's robust with respect to the uncertainty, this irreducible uncertainty. So we need an optimal experimental design under uncertainty framework, OEDUU, which, well, in general would be difficult, but we'll focus on a specific case here. And we cannot have a design that's good for every single velocity field, obviously, but then we can find something that works well in average. And I'll specify that. Okay. So formulation. So we focus on linear inverse problem, and the example of which was that inverse advection diffusion problem. And we will make some assumptions to make the formulation straightforward. But I mean, it's a common canonical case. We'll work in this Gaussian linear setting. Okay, so I have a linear forward model. F is a linear parameter to observable map. Given F, parameter M, it gives me some vector of measurements. So I have data, and this is noise, eta. As you see, the parameter is a function, so it will be an element of some Hilbert space. It will be L2 of some domain. So that's that. And Gaussian prior. Now there's some care that has to be taken on defining Gaussian measures of function space, but you know, maybe I can give some reference for that, but we'll not discuss much. And we have additive Gaussian noise. And as is well known, in such case, their posterior results are Gaussian, and you have this nice expressions for the mean and the posterior covariance operator. So this mean of the posterior, in this case, is the map estimate. You have the expression, and then this is the posterior covariance. Now you might be wondering, why do I have these additional spaces? And maybe some mistake in my LaTeX code, but it's not true. Actually, this is by design, because, well, we also have to consider this additional model uncertainty when we look at this Bayesian inverse problem. And in particular, we will focus on this posterior covariance operator that, you know, will allow us to find some quantify uncertainty. And so this C appears in general in some nonlinear way in the forward model. So F is the forward operator, and F star is the adjoint. So, and just let's get used to, when soon we will discretize everything, we will have matrices, but every application of F to some vector will be a forward solve. So you can think of the forward PD solve integrating forward in time, and F star would be adjoint PD solve. So these are kind of expensive things to do. But that's the setup. So we have to account for this C. Now, let me go back to our OED problem. So we start with a grid of candidate sensor locations, and we have a vector of design weights. We stick these design weights on a diagonal matrix, this capital W. And solution of the Bayesian inverse problem then will depend on the design. And in particular, the posterior covariance will depend on this weights in this way. So you have this diagonal matrix of weights appearing in the bit F star F. And of course, you also have the Xi. Okay, so this is a little bit quick, but that's the posterior covariance operator in this case. Okay, so now I consider a optimal design where we want to minimize the average posterior variance as quantified by the trace of the posterior covariance operator. Right? So we could formulate that optimization problem, but the issue is that well, it depends on Xi, the solution. So for different choices of Xi, well, I can get very different designs. I will actually show you some examples. So if you want to do optimal experimental design under uncertainty, the first step is to consider a risk neutral formulation where I look at this optimization under uncertainty problem, and the goal would be to minimize the expected value of the average posterior variance. And there is the issue of this term that I didn't mention. So as I said, we need some penalty method to encourage sparsity in the design, because if I don't put in a penalty, well, one good way to get the minimize get the smallest possible posterior uncertainty is just put sensors everywhere, which, well, I mean, it's not very optimal, obviously. So we put this penalty term to encourage and control the sparsity of the design. So how many sensors you can put. And you won't have very direct control, it would be indirect control, but then you can work with this gamma, the penalty parameter. And there are different ways of doing sparsity control. I will not have time to discuss that particular aspect, but we use this technique that we came up with actually quite a few years ago at this point, where we solve a sequence of optimization problems with penalty functions that successively try to approximate the L0 norm. So, and in practice, we do get binary design vectors. So this is the optimization problem that we have to solve. Right? But now, how do you do it? Well, one thing is that this trace, the covariance operator is going to be a very high dimensional operator. As you see, I've already discretized. I'm using matrices and matrices here. But the dimension of that matrix would be, I mean, it could be quite high, because it depends how many degrees of freedom I have on my computational grid. So it could be thousands, tens of thousands. So this would be a high dimensional operator. And there are situations where people probably, inverse problem people know, when your measurement dimension is much lower than the discretized parameter dimension, which happens quite a bit, you can reformulate things a little bit. So you can do some linear algebra, and it's not completely trivial, but it's not too bad either once you know what you want to do. And we don't need the details. Let's just maybe focus on this term, where I have trace of this operator looks ugly, but I have a F star F, and if I use cyclic property of the trace, at some point I can write something that involves F star. We call this operator inside the brackets here K. Take notice that that operator now is in linear operator in the measurement space, so it has the dimension same as a measurement. So you can, instead of optimizing the trace of an operator on a full parameter discretized parameter space, by doing some linear algebra, some care, reformulate it in this measurement space. So I don't have to, I can just estimate the trace maybe directly, because it's not going to be a very high dimensional operator. Okay, so that's one problem structure that can be used. Now, so let's take a look. How do I calculate this trace? Well, I could just, well, okay. I keep skipping. So another thing, so we have to optimize the expected value of some this operator K, where expected value is taken over C. So you can use either stochastic approximation or sample average approximation. The latter is what we use. So we use a SAA approach. We fix a sample of the X's, the sample of log-permeability fields, and then we get the corresponding velocity fields as such, and then the goal becomes to solve this optimization problem where I've replaced the expected value by the sample average. Okay, so that's the sample average approximation. Okay, so that looks like something that we can now do on a computer, except there are additional challenges. So how do you calculate this trace? Just have to add up the diagonal entries, right? But applying this K on vectors is very expensive. So you need to, and then you have to repeat this n times for each of the SA samples. So you need the applications of K. Remember, K had F and F star, and then there was this, right, F and F star. So that's 2 PDE solves. And then there's this S inverse, but S also contains 2 PDE solves. So each application requires 2 PDE solves plus applying inverse of an operator containing 2 PDE solves. Too many PDE solves. And you have to repeat all these calculations at every step of an optimization algorithm. And I haven't even told you about how to calculate the gradient and such, but that has cost too. So we have to do something, otherwise it will be impossible to do this on a computer. So one possible thing, something we tried in the past was when we didn't have additional model uncertainty, we just had one copy of F. We just calculate the low rank SVD of this operator F tilde. This is this forward operator preconditioned by the square root of the prior covariance. But here we have multiple copies of this Fi tildes, so that will not be very tractable to compute all these SVDs and store them and keep track of those singular vectors throughout your optimization. So a more reasonable approach would be just to maybe, at the cost of course, some approximation errors, not optimize, don't do an exact rangefinder for every FIs, but find this space which captures, roughly speaking, effective composite range. So this is how we do it, and more details, of course, is in our paper. You operator this matrices Q and Q hat. These have orthonormal columns, and you consider this type of approximation, and that can allow you to, of course, we will not do this, we will just calculate this approximation, and then we can use this in place of F tilde i's during the optimization. So if we can do that successfully, then you don't have to solve any PDEs during the iterations of your OEDUU optimization problem. So that would be of interest, of course. One more issue that we encountered is, well, computing this Q star F tilde Q hat requires K PDE solves itself. And well, if K was big, remember K was this dimension of this composite, effective range space. So one thing we found helpful was to cluster similar velocity fields and then calculate composite ranges corresponding to each cluster, and that helped to reduce the number of PDE solves. Now I'm skipping details, obviously, but one thing that I will point out is the choice of the distance that you use for the, during your clustering is kind of delicate, so that requires some care. You can look at how we did it in the paper, but that actually helped to compute this approximate surrogates, let's say, for F tilde i's, but in a more efficient way. So if you put all of that together, then now I can finally show you some numerical results. So let's go back to our advection diffusion example. Here, I'm giving a little bit more detail. So we saw the advection diffusion equation as before. Now I have some boundary conditions. That, of course, also is important, but that's some modeling stuff. The setup of the problem, we have a grid of 234 possible sensor locations, velocity field samples. We have some velocity field samples. Actually, I don't remember. I think N was maybe 100, but we can look. And goal is to find the subset of locations minimizing the optimal criterion under uncertainty. So we want to minimize the expected value of that trace of the posterior covariance. A word about the computations. This was done with Phoenix and HippieLib. Some of you might be familiar. If not, this might be worth a look. Some work going back to the group of Omar Gattas and Noemi, Petra, and Umberto. Yeah, so we did the coding there. Now, let's just do what I wrote as bad idea. So if I just, for each choice of velocity field, I just do a traditional OED problem. I compute a optimal design. As you see, so I have different X's, if you wish, and we solve the sensor placement problem. And as you see, they're all over the place. So this doesn't sound like a very good idea because, well, if most of them were clustering in some places, maybe that's good, but doesn't sound like a very good idea. And I will also show more results. So that's not something we want to do, but OEDUU, we will do what we discussed earlier by minimizing this expected value of this operator. And yes, we use this regularized L0 sparsification. So we use a continuation approach and all for sparsity control. We use gradient-based optimization, BFGS. Number of minimization problems that we solved with our continuation was about 10. Take notice though, once we do this low rank approximations, then we don't have to do PDE solves in the optimization iterations. All right, so here's a plot that is like a check your answer plot where what we did deterministic OEDs with corresponding to different realizations of the velocity field, and then OEDUU with 100 samples. And then we forget about the samples used, the training or computation of the design. We went and generated the first set of, I think, 100 or so realizations of the velocity field and calculated the expected value of this K using the OEDUU designs, if you wish, and this deterministic designs. And as you see, I mean, we expect this red line symbols that correspond to OEDUU always be below, but of course we do approximations, there's sampling errors. But you see, we consistently do well with this red designs, and with the blue dots, the deterministic OED, which you can also consider as like doing expectation with just one sample. Yeah, you can get lucky and get some okay design, but you could also have like very, very suboptimal design. So that's not a very good idea in practice to just use some random sample of velocity field to calculate the design, unless you can afford to put too many sensors, in which case then maybe that's fine. But if you have access to few sensors, then OEDUU definitely is the way to go. Now, another experiment, and this is possibly a little bit more interesting, important to test. So we at the end, when we solve the inverse problem, we don't know what the velocity field would be. Yeah, if you compute a design and you go ahead and solve the inverse problem, you quantify posterior uncertainty corresponding for data coming from some velocity field. So here, what we have calculated is the trace of the this K corresponding to OEDUU design and the deterministic OEDs with many samples. And as you see, if I look at the statistics of this quantity that quantifies the, let's say, reduction in uncertainty, I I'm doing very well in terms of, I'm doing well in terms of the mean in average, and also the spread. So this is like, I think 5% to 95%, 5% percentiles to 95th percentile bounds. This is what the shaded regions show. So this OEDUU gives you a design that in average is good, but then also the spread of this distribution is also smaller. Again, it's a little bit fast, I understand, going through these results. These are just some things we did, and we have a lot more in the paper, of course, you can look to show that, yeah, it is important to account for the uncertainty in the modeling parameters. In that case was the velocity field, which you have a lot of uncertainties, and you get designs that well, give you much better quality data, more robust with respect to uncertainty rather than just taking some chance. So this is just some illustrative example. And now I see I have time to maybe discuss the nonlinear stuff a little bit. Not too much, but maybe I can stop here. If you have questions, maybe you can ask, because I didn't hear anything, or maybe we can just leave the questions at the end. Not sure if questions at this point.
I do have a question. I didn't quite, maybe you said it and I didn't notice that. Do you model your the prior distribution of the source of your contaminant?
How do I? Well, we just use the Gaussian, which I understand physically that's not the best idea, but just to stay in the frame, this Gaussian linear setting, yes. I didn't give the details, yeah.
But then when you do your simulations, you just consider the, how do you consider the, you don't have to sample from your prior in this sense and then simulate your model with different sources of locations of the contaminant.
No, okay. Yeah, I see I think I understand your question. So this is a linear setting. So I actually have a closed form expression for the posterior covariance, but in the nonlinear inverse problem, then yes, that becomes important, because I have to generate some training data, and then that we don't have to do that here.
Because your model is linear with respect to the source location.
Right. It's linear in the initial state. Yes.
Okay. Yeah, that's right. Thank you very much.
Yeah. So, and then we can have more discussion soon. So yeah, nonlinear setting. And I mean, I gave a recent talk on this on SAMUQ, but maybe we can have discussion after the talk, but I'll just maybe some broad ideas, some things that I've been thinking about, and some of it I'm doing. So let's consider this model inverse problem. It is also related to subsurface flow. Here, the inverse problem is to in fact estimate the log-permeability field, so that becomes, I mean, the forward problem is linear, obviously, but the inverse problem becomes nonlinear because the parameters enters nonlinearly. And then OED is to work to take measurements to estimate the log-permeability field. But as you see, we have a lot of, even though it's the simplest case, you have a lot of quantities here. You have the source terms, you have to specify boundary conditions. So there could be a lot of sources of uncertainty in the inverse problem, in addition to this M that you're trying to estimate. So, and combine this with the fact that it's a nonlinear inverse problem. So trying to design experiments under uncertainty in all kind of modeling parameters could be quite challenging. So some of the ideas I have been with some collaborators, obviously, considering is, for one thing, could we do some sensitivity analysis? And when we talk about sensitivity analysis, a lot of cases we're thinking of sensitivity of the forward problem to parameters, like some Soul indices or derivative based or whatnot. But the sensitivity analysis here I'm talking about is to assess the sensitivity of the solution of the inverse problem to modeling uncertainties. Now that's a little bit more straightforward to discuss for deterministic inverse problems, because I could just, the solution of the deterministic inverse problem is just a minimizer of some, regularized data misfit cost function also, and I could do post-optimal sensitivity analysis of that minimizer with respect to modeling uncertainties. And that could be useful because then you can figure out which of the model uncertainties are important. And then later downstream, you can incorporate those uncertainties that matter in the OED problem.
Can I ask you one question?
Yeah, yes, please.
Yeah. Regarding the functional, right, that you're minimizing there, so the penalization is understood as a Tikhonov penalization, or you have in mind some prior for the parameter n that gives this?
Yeah, it's a good question. So here I just stated the deterministic version of it. So in this, that's just a deterministic inverse problem. In a Bayesian formulation, then I have to pay attention to that term. It will come corresponding to some prior, but then that might actually need to be modified in a Bayesian setting. But that's the type of thing I have to do when I solve the problem for the map point. So I have to properly.
That's what they expected the map, and they expected the other to come from the prior, right? That's
right. That's what will happen when you for the map estimation problem. But yeah, this is just illustration right now. It's just the deterministic version of it. But yeah, that is correct. So this will depend on the prior covariance. And then obviously in the Bayesian setting, I also have to weight this appropriately with the noise. Did I answer? Yeah.
Sure.
Yeah. So, and how do you do OED? Again, it's kind of fast, but I do have some papers on sensitivity analysis of inverse problems I'll mention, but OED of nonlinear problems under uncertainty, I'm doing it now. So I don't have a paper to point to myself, but there's some other works out there. But one thing that I learned about recently is this Bayesian approximation error framework, the so-called BAE framework, where it gives you a systematic way to incorporate model error or model uncertainty in your formulation of your Bayesian inverse problem. And then building on that framework, we can come up with the OED formulation, or formulate the OED objective that is so-called uncertainty aware. If you think about it, the way I formulated the OED problem for this linear case, and I could do it for nonlinear case too. We did the optimization under uncertainty when we had the integral outside. In this BAE framework, you're essentially pre-marginalizing the model uncertainty, but that requires some further discussion that maybe we can talk about because I think we'll have some time for discussion. So yeah, these are some ideas to tackle such problems, because just formulating a standard optimization under uncertainty problem for the design of nonlinear inverse problem could be quite challenging. It's worth exploring, I think. Maybe some stochastic gradient descent approach might work, I don't know. But this BAE approach seems promising. And just to mention, if people are not familiar, there are of course other papers on the BAE, but this particular problem, my colleague Noemi and some collaborators, of course Kaipio is there, and Rue Nicholson, they wrote this paper in inverse problems. This is a PDE-based inverse problem, so if you're used to that class of problems, it's a nice paper demonstrating the BAE approach, not for OED, but just for the parameter estimation. So let me go ahead and summarize, and then we can discuss more. So I discussed optimal design of linear inverse problems in presence of irreducible uncertainty. where let's remember that this is a type of uncertainty that you cannot reduce by parameter estimation at the point where you're considering the inverse problem. So it could be some aleatoric uncertainty that you can never reduce anyway, or it could be some epistemic uncertainty that possibly you have reduced before or not, and that, but at the point of solving the inverse problem, we're just stuck with that. So that I call irreducible. And you saw even in the linear setting, it was quite complicated. We had to do a lot of approximations to be able to solve that problem on computer. Remember, we're considering very high dimensional inverse problems. These are the parameters are discretizations of field quantities, so quite high dimensional, and then your forward solves are expensive. So even in the linear setting, we had to overcome a lot of challenges. So the ongoing stuff is the design of nonlinear inverse problems, and I'm considering the BA framework and sensitivity analysis to detect source of uncertainty. This sensitivity analysis, let me first talk about the references. The references for this talk that this OEDUU under uncertainty of the linear stuff are irreducible cases. This paper that I wrote with Karina Koval, who credit to her, she did pretty much most of the coding for that paper, and my colleague Georg Stadler. So that appeared in inverse problems, and this is might be helpful to get started on, or one possible choice for design of inverse problems, Bayesian inverse problems governed by PDEs. That's the linear setting. So that's another appropriate reference for this talk. But yeah, so just some related references. Let me just mention this other paper we wrote recently. That's the design of large-scale linear inverse problems under reducible model uncertainty, where the additional uncertainty, in fact, was part of the inverse problem, but we wanted to find a design that minimized the uncertainty on specific parameters of interest. So that paper appeared in JUQ. There again, we considered a simple case, so it's all linear. So we had a linear dependence on the inversion parameters and linear dependence on the additional uncertainty. So there we could do exact marginalization and then come up with the uncertainty over design criterion. And that's kind of related to what somehow is done in this BAE framework, where we still want to pre-marginalize, but except things are nonlinear, so we have to do a lot of approximations. And the sensitivity analysis, yes, I'll get back to it. We call this the hyper-differential sensitivity analysis. This is collaboration with colleagues from Sandia, Bart Van Bloemen-Wanders, and Joey Hart. And Isaac Sunseri was one of my grad students. And we have another paper too. But this one would be a good one to start if this piques your interest. There we actually systematically show how do you formulate the sensitivity analysis problem when you want to do post-optimal sensitivity analysis of the solution of the inverse problem, and then how do you compute it, because it's quite expensive. We also have a recent work on the hyperdifferential sensitivity analysis for Bayesian inverse problem. That one, if you're interested, email me, or well, maybe my Google Scholar, that we just submitted very recently. That one, we considered a Bayesian setting and try to do sensitivity analysis of some quantities of interest derived from the posterior distribution. So I think at 10:47, I think I'm going to stop here.